Hello friends, welcome to my channel. Let's have a look at today's daily challenge problem, problem 1061, lexicographically smallest equivalent string. In the current video, we are going to explain a method based on unified or equivalency disjoint set and data type. So first, we are going to read through the problem statement to digest the requirement, and then we do the analysis and do some comments, and finally we share the code. And in a follow-up video, we're going to explain another method based on graph traversal. First, for now, let's look at the problem statement. We are given two strings of the same length. The two strings are S1 and S2, and also we are given a base string. So we are required to return the lexicographically smallest equivalent string of the base string by using the equivalence relationship induced from the two strings S1 and S2. So the equivalence relations are induced from the equivalent characters in the corresponding strings S1 and S2, right? So notice that for equivalent relationship, there are three defining properties. One is reflexivity, the other is symmetry, and the third one is transitivity. So this is actually a very important mathematical concept or logical concept. So here are three examples. Let's look at one of them. So let's look at example 1. So from the equivalence or equivalent characters by the correspondence in S1 and S2, so we can group the corresponding equivalent characters like this, right? And then we can replace the corresponding characters in the base string with the corresponding smallest one lexicographically, right? So for example, P is replaced by M, and R is replaced by K, right? So the output for this one is M, A, K, K, E, K. So with this done, let's also look at the constraints. First, the length of S1, S2, or the base string are bounded above by 1000. So 1000 actually is not a very large number. So secondly, so the two strings S1 and S2 have the same length. So thirdly, S1, S2, and the base string consist of lowercase English letters. So here actually there is an indication, because we know that there are 26 lowercase English letters. So with that said, let's look at the treatment in the current video. So in the current video, we're going to explain a treatment based on the unified method. So in unified also actually are associated with the disjoint set abstract data type. So our plan is to solve and explain this problem with the help of unified method. So typically in a unified implementation, we use two attributes. So let's say one is roots and the other is recs, or similar names as you like. So in this specific problem, actually we could just use one attribute, roots. The reason is that we could use the root as the lexical order as rec. So let me repeat. So here we can use the root as the rec. So actually what we used is the lexical order. So this point will be clear when we see the implementation. So before we do the implementation, let's first share a walkthrough for an example. So this one is the one in the main statement. So we have S1, that is ABC, and we have S2, that is CDE. So the base string is EED. So from S1 we know, so A from S1 and S2, so we know A and C are equivalent characters, right? A and C, and B and D are equivalent characters, and C and E are equivalent characters. So therefore, by the properties of equivalent relation, so we know ACE are all equivalent characters, and BD are equivalent characters. So because we want to find the lexical smallest one, so we can, for each of the two clusters, we can assign them a representation or delegate. So here I'm going to use A. So here I'm going to use B, right? So therefore, AAB is a lexically smallest string due to the relation A and E are equivalent, B and D are equivalent, right? You can check here because E has representation A, right? D has representation B. So with that done, so let's make some comments. First, in this video, we are going to first implement the disjoint set data structure, and then our implementation will be tailored to this specific problem. And then we are going to do the problem logic, which is very straightforward. Second comment is that, so in fact, this problem can be cast into a graph problem. Then one could get all the connected components and then find the lexical smallest string for the given base string. As for finding connected component, so this is actually a very common or routine task for which we could use depth first search or breadth first search. In other words, we can use any traversal. So we will do this format of coding in a follow-up video. So with that said, let's look at the implementation. So here, actually, typically there are two ways. So we can implement the disjoint set data structure inside the function signature, or we can implement a separate class. So here I'm going to choose the latter. The reason is that we want to demonstrate this abstract data type as a whole and also for general purpose. So here I'm going to implement this DFU. So here I'm going to initialize this. So typically, as we mentioned, we're going to use roots, right, and also self racks. So typically the rack will be the cluster size. So here for this problem, we want to use the lexical order of the characters. So I'm going to use the root and compare their lexical order. So I do not need this racks. Or you can see we use the root as the racks. So with that said, so this finishes the initialization. So next we are going to define the find method. So we're going to give a character, right? So we want to find its root. So for this, notice that our initialization, so or instantiation, so dictionary is empty. So we need to treat this case when we do the implementation. So we are going to do this for if character not in self roots, then we are going to add this self roots character equal to itself, and then we are going to return this character. So this is the one case. Otherwise, if character is a key of self root or inside this data structure, then we are going to introduce a variable called result, and then we are going to do a while loop. So if self roots result does not equal result, then basically what we are going to do is we are going to set the result to be self roots result. So this is what we want to do. So here, this is very vanilla. So we are going to return result. So because after this while loop, so we always end at a state that these two, the roots of result and result are the same. So here we are going to use a path compression to accelerate the procedure. So basically we are going to apply self roots operation in both sides. Self roots. So this is not absolutely necessary for this problem here, but we want to add this here just for general knowledge or for acceleration. We can see this. So this we are going to return the result. So this is an implementation for the find method. So next we are going to implement the uni method. So we're going to uni character 1, character 2, right? So first because we have already implemented the find method. So let's first get the corresponding roots. I'm going to call it R1 and R2 equals self find C1 self find C2, right? So if R1 and R2 are the same, we do not need to do any operations. Otherwise, if R1 does not equal R2, it means that for present C1 and C2 are not connected or lies in different branches. So what we are going to do is so here typically we are going to use rec, but for now we just need to compare the lexical order and use the lexical order as rec. So if R1 is less than or equal to R2, so here the less than or equal to it means that lexicographically R1 is smaller than R2, right? In this case, so we're going to set the roots of R2 to be R1 because the problem prefers that the lexically smallest one, right? So otherwise, what we do? Otherwise, so we're going to set self roots R1 equals R2. In other words, we want the smallest one. So that's it for the union, because the union is just a operation without any return. So that's actually the implementation of the disjoint set data structure for this problem here. So notice that we just have one attribute roots. So here, when we do the union by rec, we are using the lexicographical order. So with that said, we are ready to do the problem logic. So for the problem logic, so it's actually very straightforward. Let me first DSU. So let's DSU. Let's instantiate a object, and then we're going to check the equivalent relationship. So for C1 and C2 in zip S1 and S2, right? So notice that here we're using the zip function. And then what we are going to do is DSU union C1 and C2. So this way, actually, we know C1 and C2 are in the same cluster. Because when we do the union, we also reset the representation or delegate of the cluster, right? The corresponding cluster C1 and C2 in. So that's it for the problem. And next, we just need to find the lexicographic smallest representation for this base string. So this is actually one line. So here we are going to use the join method for string, and then we are going to use a list comprehension. So what we are going to do is to find. So let's see, DSU find the representation for this character, for the character in base string. So that's it, right? So this way, so the find will find the roots or the delegate of the corresponding clusters, connecting components, or equivalent characters for the character C. Right? Then we find the smallest one, and then we join. So the reason that we find the smallest one is due to the fact the way we implement the union method, right? So here we are using the lexicographic order, or we can see we use the character order, right? So that's about it. So for this problem logic. So I guess for now it's good to do a test. Let's see. Yeah, it passes one example. So now let's look at the generic case. Yeah, it passes all the generic cases. So I guess that's about it for this problem with the current method. In other words, the disjoint set method. So here, let me give a quick summary. So what we did is actually the following. First, we implemented a disjoint set data type, data structure, and then we encoded that with the problem logic and do the return. So with that said, I guess that's about it for this video. So in a follow-up video, we're going to explain the traversal-based method for this problem. You're welcome to check out. And meanwhile, we have a playlist for using a union find method. You're also welcome to check out that or our channel. Thank you.